Hello and welcome to this feature of the week video. Today you will learn what's behind the linearization toggle, which is below the standard errors and likelihood task. In the video number 145, you learn how to estimate standard errors with the stochastic approximation, and in the video 147, how to calculate likelihood using the importance sampling method. In both tasks, the difficulty lies in the calculation of the log likelihood. That is the logarithm of the probability p to observe the data y for each individual, given the estimated population parameters theta. If the observations follow a normal distribution, then the probability density function is easy to write. But the problem here is that we don't know the true individual parameter psi, so the PDF does not have a closed form. To overcome this problem in the stochastic approximation, the Fisher information matrix is represented as a combination of conditional expectations which are based on the first and second derivatives of the likelihood. In the importance sampling method, we integrate over all possible values of individual parameters and express this integral as an expectation. In both cases, we approximate the expectations with a Monte Carlo procedure. Now, in the linearization approach, the true individual parameters are still unknown, but we assume that they are not too far from the empirical base estimates, that is EBEs. The key step is the Taylor expansion of a function. If we know a value of a function at a point x0 and its derivatives at this point, then the following infinite series gives its value in the neighborhood of that point, let's say at x0 plus some delta x. Linear approximation means that we use only the first order term of this series. In the calculation of likelihood, linearization is used to approximate model predictions f at the true value of the individual parameters psi, which we assume are in the neighborhood of the EBEs. And the EBEs are known because we can calculate them with a dedicated task in Monolix. To make the first step, we can rewrite psi in this form to have the known value psi EBE plus a term that is small. Then we apply the linearization with the EBEs being x0 and psi minus psi EBEs, the small perturbation delta x. The derivative here of the function f is with respect to the individual parameters. Let's consider individual parameters with a normal distribution. In the absence of covariates, we can write psi as a sum of the population value, psi pop here, and random fx eta. Inserting this into the formula for y and reorganizing the terms, we can separate a fixed term lambda and a normally distributed random variable with standard deviation gamma. Here we know all the components to calculate lambda and gamma. It means that the observed data for each individual are approximated by the normal distribution with a mean lambda and a standard deviation gamma. Now we can easily calculate the probability of the observed data using the formula for the probability density function of a normal variable. These formulas include derivatives of the structural model F. This function may be the solution of an ODE system that does not have a closed form solution, so Monolix approximates them numerically with a second-order centered finite difference. To calculate the Fisher information matrix, we need to calculate the first and second derivatives of the log likelihood with respect to the population parameters theta. They are also obtained with centered finite differences in Monolix. Now we know everything to calculate the probability p to observe the data y for each individual, given the estimated population parameters theta. We obtain the log likelihood by summing the logarithm of this probability over all individuals, and we calculate the standard errors in the same way as during the stochastic approximation. So the Fisher information matrix is inverted, and the diagonal element represents the standard errors. To explain you the linearization method, I used a normal distribution for individual parameters to simplify the notation. But linearization works in the same way for any monotone transformation H of individual parameters, such that the transformed parameters are normally distributed. Psi bar here is a predicted value, which in the absence of covariates equals population value. In case of normal distribution, this transformation H becomes the identity, while for the log normal distribution, it is a logarithm of psi. In this general case, if I denote transformation of psi I with zi and transformation of EBEs with z tilde, then the linearization around transformed EBEs of the model prediction F has the same formula as previously, and the observations are approximated with a normal distribution around lambda I with standard deviation gamma I. The difference here is only in the calculation of derivatives. Because we use a transformation h of individual parameters, the derivative with respect to z is a product of the derivative with respect to the parameter psi and a Jacobian of the transformation h. It is important to remember that the linearization method depends on the EBEs values. They are obtained in a separate task, so you should run it before running the likelihood or standard error task. If you don't calculate EBEs before, then Monolix will perform linearization around conditional mean if the conditional distribution task has been run, or around the mean from the last SAEM iterations, and in both cases the estimates are less precise than with the EBEs. So when is it useful to calculate likelihood or standard errors with linearization? Linearization is much faster, so it is a good method to start for rapid selection of models. However, it is available only for continuous data, and it tends to be less accurate with respect to other methods. Thank you for listening and have a good week.